In Physics 141, you're either analyzing the position or the momentum and energy, and these items right here are subject to the conservation laws. So sorry about the writing here. You're either doing that or you're looking at the rate of change of these items. So, for example, for position goes from looking at the x value to basically velocity and acceleration. So this is, you're looking at the change in position with time, and this is in the general category of motion. And for this course, there are really two cases. There's a linear motion, and that's 1D and 2D, and there's rotational, and that is pure circular motion or a combination of kind of running around a track, something like that, not just in a circle. So in the set of conservation problems, you looked at conservation momentum, which is around collisions, and you had two types of collisions. You had elastic and you had inelastic, and the conditions around those, of course, are different. In the inelastic collisions, you know that both cases momentum is conserved. In the elastic, the energy is conserved. In the inelastic, some of the kinetic energy is lost to heat. So a special case of momentum or changing momentum, a change in momentum with time, is actually, I'm pulling out the mass here, mass times the change in velocity with time. You may recognize this essentially as F equals ma. And again, two cases. There's linear. This is supposed to be linear. F equals ma. And there's rotational. I'll just put ROT. And that is tau equals I alpha. Again, these are vectors here. F, A, and alpha, and tau. Let's see. Down under energy, you recall that the guiding principle there is that the total energy is equal to, this is supposed to be TE, equals the sum of potential energy plus kinetic energy plus any work that is done. Oops. I'm going to leave that, in this case, potential plus kinetic. And you have, for potential energy, you looked at two cases. You looked at the gravitational potential energy, U equals mgh, and then you looked at the case of elastic potential energy in a spring, where U equals kx squared over 2. And kinetic energy, you looked at basically linear, and you looked at rotational kinetic types of kinetic energy, and you know the equations for those. Linear being 1/2 mv squared, and rotational being 1/2. Now, the mass equivalent in rotation is the rotational inertia, and then v squared would be replaced by omega squared, the angular velocity. This is totally unreadable, but what I'm trying to do is give you sort of an organizing frame so that you could see how all of this class stuff fits together. So we're looking at analyzing three things: position, or these quantities, momentum and energy, which are conserved, and then the rate of change of those. So the rate of change of momentum is simply these force relationships, and then the rate of change of energy is simply power relationships. So if we look at energy, and I'll draw the line over here, the change in energy with time is simply power relationships. And I believe you actually looked at two cases of those. You again looked at linear and rotational, where the linear is equal to the dot product of the force and velocity vector, and then rotational, unsurprisingly, the dot product of the tau. So what you might be able to see in this is a bit of an organizing frame for the different types of problems that you have done, and you'll see that the themes are within each of the problem. You're asking, are you looking at a linear case or a rotational case? A linear case or a rotational case? Linear, rotational. And this is pretty much all that you have covered in this quarter. Even the impulse comes under the elastic computations, conservation of momentum. So what I would recommend in the way of studying for the final is to take Pete's equation sheet that he provided on the midterm. He's likely to provide a similar equation sheet, and go through this set of equations and basically identify for yourself, group them under what category they correspond to, and identify for yourself what the conditions are for which they would apply. So, for example, I think this is universal gravitation, so I don't think you're actually using this or these values. I could be wrong. But there's a whole set of equations that correspond to basically motion, these equations here. And I'm going to kind of, what I would do is sort of say, okay, this is all about motion, mostly linear motion. I think this is linear motion, actually. Linear motion, and there's a particular case here. This one right here corresponds to centripetal acceleration. So, this is the case where you have actually a constant velocity. So this is centripetal. So this is supposed to be a vector towards the center, because that represents centripetal acceleration. And then the constant velocity, constant. I can't write. Constant. Circular velocity. Anyway, you get what I mean. Constant circular velocity, and then just kind of go through and identify this. So these for yourself, so you understand what the equations apply to. So these equations right here all refer to computations around the rotational inertia, and so again, this looks like gravity. Universal gravitation. I'm going to cross this one out because you're probably not going to use that one. So go through and create, circle the set of equations and what they correspond to. I think that would actually be, in my mind, a very helpful way to separate the different applications of the equation. And then the next step would be to go through and identify what conditions the equation corresponds to exactly. So I did that a little bit with this centripetal acceleration. I said it was constant circular velocity, or constant. So maybe I should say that. Excuse me. Constant speed. So the magnitude of the velocity is the same, and that causes the centripetal acceleration. So this, for example, is the case of the force. This should be F equals negative kx, I think. This is a force of a spring. So you'll see, you'll recognize these equations, but go through and write down what cases they apply to. And you should find that you will actually have just a number of groupings that are finite, so you'll be able to recognize the major themes that are inside this equation sheet, and that will help you when you get the test, and you won't spend time sort of trying to orient yourself around the equations.